Hey everybody, Matt here with LGN Tutoring. Today I'm going to be going over an example problem for thermodynamics, which has to deal with energy and energy transfer. So we'll jump right into it. Wind is blowing steadily at a certain velocity. The mechanical energy of air per unit mass and the power generation potential are to be determined. So I already drew up the schematic for the system. This is actually where we're getting all our givens. So we know that the wind turbine has a radius of 60 meters. The wind is steady, meaning it's not changing over time. And we're going to assume that it's the same everywhere, and it's going to be 10 meters per second. Now, the density of air is also a given, and in this specific book, it is 1.25 kilograms per meters cubed. So, right now, I just want to go over, there's a lot of different V's that are going to occur throughout this problem, and I don't want to use the same V, that way you guys get confused. So, whenever I use a V that looks like this, that stands for velocity. Ooh. Velocity. Velocity. Can't spell today, apparently. And whenever I use a V that looks like this, that is volume. Just doing that in an attempt to try and alleviate some possible confusion that could occur. So, we can jump right into it. The first thing we wanted to find was the mechanical energy of air per unit mass. So in order to do that, I'm going to grab a new paper. In order to do that, we have to find the mechanical energy of the system. So we just do E mechanical. Now the only energy in this system that is occurring is within the windmill, and it's through kinetic energy. So we want an equation for kinetic energy. Now the equation for kinetic energy is pretty simple. It's velocity squared over 2. Now we know that the wind is moving at 10 meters per second, so we can plug that in. That's all we have to plug in, actually. 10 meters per second squared over 2. Now, this will give us an answer in the form of meters squared per second squared. And that's not really what we want. We want the energy. So in order to get energy, we can multiply it by 1 kilojoule per kilogram over 1,000 meters squared per second squared. So we want the energy per unit mass, which is this. And what this is giving us is meters squared per second squared. So it's just a simple conversion. That way we get the answer we want to get. And the answer we want to get ends up being 0.050 kilojoules per kilograms. Now that is the mechanical energy, that is the mechanical energy of air per unit mass. So another thing we want to find is the power generation potential of this system. So in order to find that out, we have to do a little bit more work. Now we'll still use this number. We have the energy per unit mass. Now what we want to know is the mass flow rate, like how much mass is going through the system per unit time. So like how much is going through at any given instant. So we want the mass flow rate is what we want for this, which will be the density of air times the volume of the air going through it times the area of what it's going through. So we know that the area of the windmill is theoretically a circle because they spin and they're in a circle. So we can just simplify this to P times the volume times pi d squared over 4. Now, we know that the density of air is 1.25 kilograms per meter cubed. And we know that the velocity Oh, that is velocity, not volume. Ugh. It's actually velocity still. I'm dumb. Because that's the 10 meters per second. I didn't need to have different V's. I was so focused on making you guys not confused, I just confused you. This is actually velocity, not volume. I'm sorry. I apologize. But that doesn't affect the problem yet because 10 meters per second. There we go. I don't know what I was thinking. It's the area that... we don't need volume for this. My bad. I don't know what I was thinking. Anyways, so 1.25 kilograms per meter cubed times 10 meters per second times pi times the diameter, which is 60 meters, squared over 4. So if we plug this into your calculator, you'll end up getting 35,340 kilograms per second, which is what we want. So now, what we really wanted was the power generation potential. So what this is, this is the mass flow rate, how much is going through at any given time. What we want is the amount of energy that this amount of mass going through would produce. And we've already found all the numbers we need to calculate it. So we want the maximum work this system is producing, which is basically the flow rate of mechanical energy through the system, because that's the only way energy is moving right now. And in order to get that, all we need is the mass flow rate times the mechanical energy, which we've already calculated both of these. So it's real simple. So it's 35,340 kilograms per second multiplied by 0.050 kilojoules per kilogram, which will end up getting us 1,770 kilowatts of energy. So that is the power generation potential. All right.